All right, let's get talking to something really important, that is working with absolute value. I've been looking forward to this pretty much all day, so I'm excited I get to finally talk about it. Absolute value, just remember, what is it? It's when we have these bars, you might have some kind of number in here, right? What is absolute value, though? That's what we're going to answer today. So we're going to take a few stages of developing our understanding of the absolute value. First, we're going to look at the strict definition, the fundamental use of the absolute value operation. It's kind of like an operation. Then we're going to recap where you might have seen it, because you probably have seen it before, whether it's in Algebra 2 or Algebra 1, maybe even like a pre-calculus class. And we're just going to look at how it works a little bit. And then we're going to consider the absolute value function as a piecewise function. So if you don't remember what a piecewise function is, you'll be reminded of what that is later on in the video. So get a paper, get a pen, pencil maybe, so you can erase it. And yeah, let's get started. We're going to start with the definition of absolute value. So if we have two numbers, a and b, we can say that the absolute value of b minus a is exactly the same thing as the distance from a to b. So if we're looking on a number line, for example, and if we have a and we have b, let's say maybe 0 is over here or something. Doesn't really matter exactly where 0 is at, but this is just as an example. How would we describe this distance from a to b? Well, we would say that from 0, you can go forward by b, right? And then you can subtract this portion from 0 to a. So basically, that's b minus a. And as you can see, that's going to give us the exact distance from a to b. All right, pretty simple. The absolute value just measures the distance between a starting point and a stopping point. And we can use a number line to represent that distance. Now, since we're talking about distances can never be negative. They can be equal to 0, but they can never be negative. So I want you to realize that the absolute value of b minus a is the same value as the absolute value of a minus b, because in both cases we're going from between a and b. Now in this case we have that a is the starting point and b is the final point, and in this other case we have that a is the final point and b is the starting point. But no matter where you start from, if you're going between a and b, you're covering the same distance, okay? So even though the number line exists with positive on the right and negative on the left, if we go from b to a, we're still covering a positive distance. You could just say that our position is getting negative because it's going in this direction. But the distance that we actually cover is still positive. Okay. So that's kind of a basic definition of absolute value. Now, let's talk about where you probably have already seen absolute value before, and we'll do a couple really basic examples just to remind you how it works, in case for some reason you're not familiar. So you're most likely first introduced with using absolute value whenever we had the absolute value of a single number. And in this case, we're finding the distance from 0. How far is the number from 0? So some examples that I'll write up here is like absolute value of 5. Well, that's just equal to 5 because 5 is 5 numbers away from 0. Now, what about the absolute value of negative 6? Well, that's going to be equal to positive 6 because even though on the number line, negative 6 is on the left, which is like, to the negative side. This distance, though, is 6. The negative would just kind of refer to like which direction we're going in, but the distance doesn't care about which direction we're going in. Right, so what other number is also a distance of 6? well, that would be positive 6. And I don't know that I drew this to scale properly. But basically what I'm saying is if we go the same distance, but in the positive direction, it's like adding 6. And if we go that distance in the negative direction, it's like subtracting 6. But in both cases, we're traveling the same distance. Okay. So really what we're looking at when we do the absolute value of a single number is we're just finding the distance from 0. And so you can kind of think of our starting point as 0 if we want to use our b minus a definition. So one thing to notice is that the absolute value of a negative is the same as the absolute value of that positive number. So let's see how that works here. Let's say we have negative a. A can be any number. Well, that's going to be the same thing as negative a minus 0. But since we mentioned earlier that the distance from a to b is the same as the distance from b to a, then we can say that this, from 0 to negative a, is the same as the distance from negative a to 0, which leaves us with the absolute value of just 0 plus a, or just the absolute value of a. So it's kind of as if like the a and b is just 0 and whatever number we're looking at. And that tells us that the absolute value of the negative is the same as the absolute value of the positive. That's kind of what I showed you on the number line above as well. But I wanted to put it in symbols so you can kind of see how that's working. Okay, now you might have seen a situation where we're solving absolute value equations. And you might remember, if you don't, this is a reminder, that you kind of have to like solve these twice. What do I mean by that? Well, here's what I mean by that. If we have this equation which says the absolute value of 2x minus 7 is equal to 15, well, there's two possibilities here, okay? It's possible that the stuff inside is just literally equal to 15. And then when you do the absolute value of 15, it doesn't change it at all. So it's possible that this thing inside is just literally equal to 15. But it's also possible that this thing inside of here is equal to negative 15. Because if this were equal to negative 15 inside, and then we took the absolute value, it would for sure turn into positive 15. So we have to consider those two possibilities, right? What does the absolute value operation do? Well, it leaves a number alone if it's not negative. So if it's equal to 15, it's just 2x minus 7, nothing changes. But if the inside is negative 15, then it would flip it into a positive 15. And so we have to consider that the inside might also be equal to negative 15. And we just solve those. We use the exact same method for solving. We're just starting off with different equations. So if we add 7 on both sides of both of these equations, kind of solving them both at the same time. And then we have negative 8 here. And we use the same step on both equations again. We're going to divide by 2. Because you'll see that we started with the same expression, 2x minus 7. So in order to solve for x, it's the same procedures. So x could be 11, or x could be negative 4. It's usually a good idea to check your work when you're doing absolute value equations. Oops. Let's see, this is usually something that you'll really want to do when you're looking at inequalities. Working with absolute value inequalities. Okay, so yeah, we can just kind of quick check that in there. Plug in 11, go ahead and do that. You should get 15, and the absolute value of 15 is just 15. And then go ahead and plug in negative 4 as your x value, and you'll get negative 15 inside, but once you take the absolute value, you end up getting a positive 15. So those are your two solutions. All right, now we're going to step into something that's a little bit more advanced, which is looking at the absolute value function as a piecewise function. Remember, what is a piecewise function? A piecewise function is when we take several different pieces, it could be 2, it could be 3, it could be 4, and we create a function which exists in pieces over a certain domain for each piece. And altogether, let's see, I'm going to put f1 of x, f2 of x, and we have domain 2, and you can have as many pieces of this function as you want. It's just potentially not going to be connected. There might be like a bunch of fragmented pieces, or if it's designed carefully, they'll be connected pieces. When we talk about an absolute value function, let's review the parent graph. It's kind of a V shape, right? Looks sort of like this. That's more or less what the absolute value function of x looks like. That's just a parent function. But what's really happening here? What's happening is there's a positive portion of the graph, and then there's this potentially negative portion of the graph. What do I mean potentially negative portion? Well, if we ignore the absolute value symbols for just a moment, then we would get a graph which looks more like this. It'd be a linear equation with a straight slope upwards of 1. But since we're looking at the absolute value, we get this positive section only because what happens is this negative space, which I've sort of dashed, it's not a bold line, it's just a red dash. That's going to get flipped up into the positive because that's what absolute value does, right? It turns negative values into positive values. And so we're going to have two separate portions, two separate pieces of graph. Let's look at how we'll define that. What we need to do first is we need to make some consideration about the absolute value function. We need to ask ourselves just one more time, how can we describe what the absolute value operation is actually doing to the input values of the function, right? So let's look at this line again. What did it do? Well, when the graph would be, I'm going to erase the absolute value again. When the graph would be negative down here, that's what x, the graph f of x equals x would look like. It would go down. Whenever x is a negative number, the y value would also be a negative number. But because we have these absolute value bars here, it takes all of these numbers on the left side and it flips their y values. It makes their y values positive instead of negative. So we need to describe, like, where does that happen? How do we describe where that happens? I had a video on domain, so if you haven't checked that out already, check out the video on domain, because the domain is the sort of like the x space where stuff is happening for a function. So we're going to take a look at the domain, and we're going to consider the fact that absolute value is going to keep the value inside the same if that value is greater than or equal to 0. In other words, if it's non-negative. And the absolute value is going to flip the value inside to a positive if the inside is negative. So let's get a handle on how we write this. If we have f of x is equal to the absolute value of some function, g of x, we're not going to use a specific function yet. We're just going to say this inside is something. It can be anything. It could be 2x plus 5. It can be, 3x squared minus 7. It can be anything with some x in it, whatever this function is. If we want to write it as a piecewise function, it's going to be two different pieces at least. It's going to just stay the same g of x. Nothing's going to happen to it whenever g of x is greater than or equal to 0. In other words, non-negative. So this is what I wrote up here. I don't want you to think that I'm like going into something completely different. I'm just sort of showing you this, how we would write it as a function. We're going to keep the value the same if it's greater than or equal to 0. So let's see what that looks like on this function. This g of x in here, It's going to stay the same whenever it's greater than or equal to 0. That's its domain. And it's going to flip it, this thing inside of here, g of x, it's going to flip it negative whenever it's less than 0, because absolute value would flip it into a positive number, you see. So that's how we would write our piecewise function. Now that is not specific, because I didn't give you a specific function like a 3x minus 5 or something. But I just want you to understand the basics, that the absolute value flips it if it needs to, and it leaves it the same if it doesn't need to flip it at all. How do we know if it needs to flip it? Again, if the inside is positive, it doesn't need to get flipped. And if the inside is negative, then it does need to get flipped. That's why I put a negative on here, because this negative is going to flip it into a positive. And we're only doing that when we know that it's negative. So if we put a negative on a negative, it becomes a positive. That's what the absolute value does. It turns negatives into positives, and it leaves non-negative objects alone. It doesn't do anything to them. So yeah, let's take a look at an example. Here's f of x equals the absolute value of 4 minus 12x. Take a moment, write this down. The function first. You don't have to write the whole thing down first, but just write this function down. I want you to try to think about what's inside of the absolute value. What is that equation, 4 minus 12x? It's the equation of a line. It's a line with a negative slope, so we know it's going to be facing downwards. And I'm going to show you a graph in addition to writing the function out like I have right here. But first I want to focus on writing the piecewise function. So I want you to just really ingrain this into your mind, is that if this thing is positive, then it's going to just stay the same. Right? So when is this going to just stay 4 minus 12x? As long as 4 minus 12x is greater than or equal to 0, non-negative. And it's going to flip it, so it's going to call it negative 4 minus 12x whenever the 4 minus 12x is negative. It's less than 0. So if it's less than 0, we need to put a negative on it to flip it into a positive. Again, that's what absolute value does. Now these domains are not specific. So what I'm going to show you now is how to solve for these domains. How do I solve for this domain? What do I mean solve for the domain? Well, if I say 4 minus 12x needs to be greater than 0, that's true, but I don't want to describe it like that. I want to describe what I need x to be greater than, or what I need x to be less than. So basically what I'm saying here is we need to solve this inequality for x. So I'm going to add 12x on both sides. That goes away. And then I'm going to divide both sides by 12. And you should do this as well on your own. You should solve this for x. You need to make sure you know how to do that. It's just some basic two-step math here. If you choose to subtract the 4 on the other side, that's fine, but don't forget to flip the sign when you divide by a negative. So you can pause it, take as long as you need to, but what you should end up getting is x is less than or equal to 1/3. And the nice thing about doing that for one of these domains is that you don't really have to do that much work for the other one, because if this is x is less than or equal to 1/3, guess what this is going to be? This is going to be the rest of it. So it's going to be when x is greater than 1/3. And you could solve for yourself to see that, but just giving you the inside scoop that if this is saying, oh yeah, we're going to do one bit of behavior on the left side of 1/3, the other piece, the only other piece, has to do the rest. It has to cover the rest of the domain. Okay, and I actually have a picture of this graph, so you can take a look. And what I want you to focus on when I show you this graph is I want you to focus on this breaking point here. This 1/3, x is 1/3. You're going to see two different pieces of graph coming together at x is 1/3. What are the two pieces that you're going to see? Well, you're going to see 4 minus 12x, and then you're also going to see, if I work this out, you're going to see negative 4 plus 12x. Right, that's what this function is if I distribute the negative. So you're going to see those two pieces. on the graph below. There it is. Okay. Oh, I'm sorry. This is just 4 minus 12x right now. I still want you to focus on this. I didn't put 1/3 properly labeled there, but that's my 1/3, the purple line. And I did color code it intentionally here. So the blue portion is the portion that's unchanged. Let's go back up to the function to see where is it unchanged. It's unchanged when x is less than or equal to 1/3. So basically on the left of 1/3. So this piece is unchanged. Why is it unchanged? Well, because it's already positive. It's not negative. Now this portion in red, which I've sort of dashed, it's not bold, I put it there because it's going to get flipped. That portion's going to get flipped. That's the thing that we flipped, distributed the negative, and that's going to happen when x is greater than 1/3, so to the right side. So to finish this graph off, it's going to do the reflective behavior of this red dotted line portion. It's probably even steeper than that. That looks pretty steep. I think that pretty much hit the nail on the head. Okay, and it's kind of a reflected version of this. Let's erase that. Alright, we don't need any of that anymore. Okay, so is this making sense? We're looking at the graph, we're also looking at the definition of the function. And you really just have to remember, what does absolute value do? It flips stuff that's not positive, or it flips stuff that's negative, I should say. What did we just do? We just erased this thing because it was flipped from a negative to a positive. So the rest of that line is just going to be from negative to positive. Okay, great. Let's look at one more example. This is going to be a little bit more relevant in a higher level, like a Algebra 2 pre-calculus, even mostly in calculus, or if you were to take any kind of pretty serious physics and be doing calculus-based physics, that is. So if you were to do something like that, here we have f of x equals absolute value of 3x squared minus 6x. This is different. This is a step up. Now, what happens to this function? How do we break it into pieces? Well, first of all, it's going to just be unchanged. It's going to be unchanged if 3x squared minus 6x is greater than or equal to 0. If it's not negative, then it's not going to change at all. Let's notice though, how are we going to figure that out? Because we have x in two places, so we can't just like solve for the x real quick. We're going to have to use a chart. If you're not familiar with the chart, you're going to have to watch a video of mine on the chart. Maybe I've explained it to you before, but if not, then you're definitely going to want to watch a video on the chart. So we need to factor in order to use the chart. So let's at least do that right here. If I move this a little bit, then we're going to have 3x and x minus 2. So that product needs to be greater than 0. And we'll get some more specifics when it comes to that. We'll get some more specifics in a moment. Now, let's take a look. What's going to happen if it does flip? If it flips, then we're going to end up with negative parentheses 3x squared minus 6x. And we're going to graph that portion, the flip portion, if it's negative. So if 3x squared minus 6x is less than 0, or in other words, if 3x times x minus 2, if that product is less than 0, then we're going to flip it. And if you're not already keen to what this is going to kind of look like the general shape of this, it's going to be a parabola, because this is a quadratic expression. So it's going to be a parabola, or maybe I should say a parabolic shape. I can sketch it for you really quickly. That's the parabola. You'll notice that parabola is, I gave you a big hint by doing this, you'll notice that the parabola is positive in some places, 2 places, and then it's negative in between. See this portion down here? The function is negative, so we're going to explore that a little bit more carefully. Again, we're going to need a chart for this as well. And like I said, if you're not super familiar with the chart, well, you're going to have to just hang on for the ride here. You could pause the video now. You could stop the video now and go look at a video on a chart on how to do this kind of thing. But this is a technique that really should be taught better. So if people aren't really that great at it, I don't blame you at all. It's really not that much your fault. It was poor instruction, most likely. But when it comes to trying to figure out if something is positive or negative, we can easily do that if we can factor it, because we can find when this product is equal to 0, and then we can kind of play with some of the values that are near those spots which give us 0. Let me explain a little more carefully. So 3x squared minus 6x, we've factored that into 3x times x minus 2. So I have my input x. This is like a numbered line. I have my first factor, 3x, and that's going to be multiplied by my second factor, x minus 2. And when I multiply the positive or negatives, that's going to give me my final output f of x, because f of x is the product of these two, right? Okay, so what is going on with this x line? This x line is showing us where these zeros happen for each of the factors. You'll notice that when x is 0, the 3x factor is equal to 0. And you'll notice that for x minus 2, when x is equal to 2, that factor is equal to 0. So at any of those values, the entire product is 0. But what about elsewhere? Well, I won't get into the nitty-gritty of the chart. It's already labeled for you. You got to go watch a video on the chart if you want to see how it works. So anything to the left of 0 is going to be a negative times a negative, which is a positive. And then in between 0 and 2, it's going to be a positive factor times a negative factor. That's going to give us negative. And then on the right side of x equals 2, if I plug in something like 3 or 4 or anything bigger than 2, I'm going to get a positive times a positive, which gives me a positive overall. So this is most useful because it shows me that the inside of the absolute value is positive from negative infinity to 0. And it's also positive from 2 to infinity. What does that mean for our piecewise definition? Well, for our piecewise definition, what that means is that we're not going to flip it on these x intervals here. So if I want to more carefully write the function out, and I have a sketch of it down there, if I want to more carefully write this piecewise function out, I guess I'll write it this way. It's going to be normal 3x squared minus 6x, not going to be messed with, as long as x is less than 0, right? That's what this first one means, from negative infinity to 0, no brackets. But it's also going to get kept the same if it's positive when x is greater than 2. So anything bigger than 2, and this function is not going to get flipped because it's positive value. But according to this chart, the parabola would be a negative value in between 0 and 2. In fact, I kind of showed that on the sketch here. From 0 to 2, we have negative values. So what we're going to do is we're going to say, okay, this thing gets flipped. Negative parentheses 3x squared minus 6x whenever x is between 0 and 2. And what does that mean? That means we have 3 pieces of graph. Here I'll color code them. These are the blue ones that don't get flipped. This is the red one that gets flipped. Let's take a look at a sketch of the graph. So what the parabola would look like is like that. That's what the normal parabola would look like. But since we're taking an absolute value, all of those negative portions have to become non-negative. So they flip. This whole negative section down here, it flips. And that's the result. Okay, there will be some exercises associated with this so you can practice graphing, but also practice writing absolute value functions as piecewise functions. I think it's really going to strengthen your fundamentals. Thanks for sticking in there with me. Went for about 30 minutes. It's kind of right around the amount of time that I wanted this to last. So I'll see you on the next video.